member, as some of you may know. So here's the plan for this talk. I'm going to begin with a quick motivation on the physics. Then I'm going to tell you about JUNO. So I'm going to give you a broad picture about JUNO, like a bird's eye view of the experiment. Then I'm going to discuss a little bit what kind of physics we can do with this experiment, with this detector that I'm going to describe. And then I'm going to tell you about how the experiment is designed and what the status is. And then I'll just finish very quickly with a summary and some conclusions. And let me ask you, Antonio, how long should I take? Like, should I try to finish in like 50 minutes to give time for questions, or do you have a preference?
In average, we had a more or less average time of 1 hour in most of the seminar. However, we have flexibility. There is no hardly. Sorry, the time for question is about 10, 15 minutes. We have some flexibility, but it's advisable to finish in 1 hour because some people may have other commitments and classes.
Sounds good. Of course, I'll definitely finish before an hour, but maybe I'll try to finish before then, of course, to leave time for questions then. Okay, so this is the plan then for the talk. And so let me begin with a quick motivation about neutrinos. I think most of the people here are already experts on particle physics, and I can go through this very quickly. So I think everybody knows about the Standard Model, our best theory of fundamental particles and their interactions. It works too good, right? It's frustratingly good because we know it's incomplete, yet it works on pretty much every single experiment we have done to date. And there's one area where actually the Standard Model gives us a result that's inconsistent with what we see in the experiment, and that area is precisely neutrinos. And so let me just remind you very briefly about neutrinos. Neutrinos are part of the Standard Model. They're included as particles that have no mass, that come in three varieties and then interact only via the weak force. And now we know that this first assumption, that neutrinos are massless, is incorrect. But the other two, as best as we know, are still valid. Let me point out, in case there's any students, I didn't see if there's any students in the audience or not, but in case anybody's wondering how come these neutrinos are associated to each one of these leptons, the answer is quite simple. It's because whenever you have an electron neutrino produced, for example, it is produced in association with an electron or a positron, right? Also, when it is absorbed, whenever an electron neutrino is absorbed or interacts via charge current interaction, it will be absorbed in association with an electron, for example. Same for mu neutrino, same for tau neutrino. And so, yeah, that's one thing I wanted to point out. And the other thing is this fact that neutrinos interact only via the weak force, which is called weak for a good reason, because it's pretty weak. Not as weak as gravity, but pretty weak nonetheless. And so, since they only interact via the weak force, neutrinos can go through matter, can go through huge quantities of matter without interacting. And so if I take a neutrino of energy on the order of MeVs or higher, or even lower, and I shoot it towards the center of the Earth, there's a very large probability, 99.999% probability, that this neutrino is just going to go through the entire planet and just come out the other side. So we say that neutrinos are ghostly. They're like little ghosts. Because they can just go through walls, planets. They can go through an entire light year of lead. One nice feature or one nice thing that we can do with neutrinos, because of their unparalleled ability to penetrate matter, is to use them as messengers, as cosmic messengers. And for example, we can study the sun with them. And we can do all kinds of great science with them. But also one nice thing that I'm highlighting here, again, for the benefit of any students in the audience, is that you can even see the sun at night, right? You cannot see the sun with your eyes at night because the photons that we are able to detect with our eyes, those don't go through the entire planet Earth. So when it's dark at night, the photons are impinging on the other side of the Earth and you cannot see them. But neutrinos, they just go through the entire planet. And so if you have a detector that's capable of detecting them, then you are able to see the neutrinos coming from the sun even when it's dark outside. So again, just to be clear, for benefit of any students in the audience, what's happening is that neutrinos, they have their probability of interacting is not exactly zero. It's just very small. And so most of these neutrinos, the overwhelming majority of them, just go through the planet as if it wasn't there. But a very small fraction of them does interact here, 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 and in our detector. And just with that fraction of neutrinos that did interact, we're able to see the sun at night. There's a photo obtained by Super Kamiokande in Japan. Okay, so why do we care about neutrinos? Here's a bold statement. I think we need to understand neutrinos if we want to understand the universe we live in. And there's at least 3 reasons why this is so. The first one is that neutrinos can be used as cosmic and terrestrial messengers. They give us information that's complementary to what we can gain with, for example, photons or other particles that experience some kind of interference between the source and the detector. That's not the case for neutrinos. Neutrinos just go directly from their point of production to their detection. And so they give us complementary information. Of course, that also makes them difficult to detect. So there's pros and cons. There's all these many different sources that emit neutrinos. And so by studying the neutrinos emitted by them, we can learn more about them. The second reason is that neutrinos are extremely abundant in our universe. They're the second, as best as we know so far, they're the second most abundant particle in the universe. And so they do influence things like, for example, the large structure formation of our universe. It could also be, for example, that neutrinos hold the key or can point us to the answer of why our universe is made of matter and not antimatter. And finally, a third reason why it's important to study neutrinos is that something that I alluded to earlier today, they behave in a way that goes against what we expected from the standard model. That means the standard model needs to be expanded. We have clear experimental data showing so, and with the data we collect with neutrinos. And so the hope is that not only will neutrinos show us how to do this expansion that for sure we need to do, but maybe also give us a window into more physics beyond the standard model. Now, what do I say that neutrinos behave beyond the standard model? It has to do with this phenomenon of neutrino oscillations. And I'm going to talk a lot about oscillations in this talk, so it's important to make sure everybody's on the same page about this. So neutrino oscillations, again, for the benefit of any students in the audience, here's a cartoon explaining what this means. It means that neutrinos change flavors as they travel. It means that if I produce a neutrino beam of just one type of neutrino, electron neutrinos, for example, or actually, let me use a different example, muon neutrinos. Imagine these cars are muon neutrinos. As this beam propagates, if you sample the composition of the beam after some distance L, then you will find that some of these muon neutrinos now are tau neutrinos, represented by the vands here. And then if you let it propagate some more, you will see the third type of neutrino, in this case, electron neutrino, appearing, and represented here by the buses. And then if you wait even more, or if you let the beam propagate even more, at some point you will recover the original configuration. And this process just repeats itself, hence the name oscillation. Okay, so we're talking about neutrinos changing flavors as they travel. This phenomenon is due to quantum mechanics. It's quantum mechanics in its maximum splendor, as I always like to say. And it stems from the fact that the states in which neutrinos are absorbed or emitted, we call these the weak eigenstates or the flavor eigenstates. They're nu e, nu mu, and nu tau, the same states that I described briefly a couple slides before. Those states do not correspond one-to-one with states that have definite mass. The states that have definite mass, we call those nu1, nu2, and nu3. So they do not correspond one-to-one, rather they're a mixture of each other. This mixture is parametrized by this matrix called the PMNS matrix. We normally use the letter U to represent it. And I don't show you the full matrix here. The important thing to remember is that this matrix is parametrized in terms of 3 mixing angles, because we're essentially talking about a rotation in 3-dimensional space. So these 3 angles are theta 1, 2, theta 1, 3, and theta 2, 3. And then one CP violating phase delta, which if it's non-zero, it means we have CP violation in the leptonic sector. So this is a key open question, as I will mention in a second in the neutrino physics. So with this mixing framework and some assumptions, such as the fact that neutrinos propagate as plane waves, we can calculate what's the probability that if I begin with an electron antineutrino, for example, and it has an energy E and it has traveled a distance L, I will continue to detect it as an electron antineutrino. And so this probability, these probabilities in general, they always look something like this. The mixing angles always give you information about how big the effect is. In this case, we call this a disappearance because we started with electron antineutrinos, and then a fraction of those electron antineutrinos will be detected as a different flavor. And so we see, in other words, electron antineutrinos disappearing. And so the mixing angles always give you a size of how big this disappearance effect is, whereas the differences in the squares of the masses, we call these the mass splittings. These give you information about the frequency of this effect, how often it repeats itself in this L over E space. Okay. Yes, so I think I said everything here. And so there's big implications to this observation that neutrinos oscillate. It opened up a whole lot of questions, many of which still don't have an answer. So the first question that you can ask is, okay, so neutrino oscillations occur, then what are the values of these mixing parameters that you just described, the differences in the squares of the masses, as well as the mixing angles? And I just want to point out here that we as a community have made really nice progress in answering this question. We now know these oscillation parameters to a few percent, as you can see here, but we want more. We want more precision because these estimations provide important constraints for other experiments. They also provide important constraints to people doing phenomenological theoretical models to explain flavor and mass in the leptonic sector. And also because by knowing these parameters more precisely, we can do model-independent tests of the three-neutrino paradigm. For example, we can search for non-unitarity in the PM and S matrix. So we want more precision. Also, there's an open question, which is, okay, there's this delta CP. Is it 0 or not? And if it's not, then this could have big implications in cosmology. It could give us some hints as to why there's more matter, or why we live in a universe that's dominated by matter instead of antimatter. We also need to determine what the ordering of the neutrino masses is. So we know that the second mass eigenstate is heavier than the first one. By the way, I hope you can see my mouse. Let me know if not. So we know that M1 is smaller than M2, but we don't know if M3 is heavier or lighter than the M1, M2 pair. And so we refer to these two scenarios as the normal and inverted orderings, respectively. And answering this question has important implications in cosmology and also other experiments. And finally, we don't know if there are additional neutrino states. There could be, for example, sterile neutrinos, and that's another open question that could have also big implications in cosmology and physics in general. So this is where JUNO comes in. JUNO will help us answer or address some of these questions, not all of them, but certainly some of these questions. And so now let me just give you the big picture about JUNO. So JUNO is designed to observe primarily one type of neutrino, which is reactor antineutrinos. And specifically, those are electron antineutrinos, as you can see here. I remind you here that nuclear reactors are a really good neutrino source. They have many advantages. First, they're flavor pure. And what that means is that a nuclear reactor emits just one type of neutrino, electron antineutrino. That's it, pretty much. To first, second, and third order, basically. That can be seen as a pro or as a con. Here I treat it as a pro because it means we don't have to worry about contamination of other types of neutrinos. Nuclear reactors are widely available. That's, of course, a pro. Many countries have nuclear reactors. They're cost effective for us researchers because normally we don't have to pay for the construction of a nuclear reactor. We just ask permission to put our detectors in there. And then this advantage, I put it in boldface because it's one of the most important. They're extremely intense sources of electron antineutrinos. And just so you get an idea, here I have a typo. I forgot to put a over second, but a 1 gigawatt thermal power nuclear reactor will produce on the order of 10 to the 20 electron antineutrinos every second. So it's by far the most intense man-made source of neutrinos. And finally, they're pretty well understood. The processes occurring inside nuclear reactors are reasonably well understood. And so you can predict, if you know at what power your reactor is operating at, and what are the fission fractions at every moment of time, you can predict to within a few percent how many neutrinos are being emitted by your nuclear reactor. One final comment, in case you're wondering how come we produce only electron antineutrinos, this just has to do with beta decay. When you break up atoms like uranium-235 inside the reactor, the products have an excess of neutrons compared to protons, or with respect to protons, compared to where they need to be in order to be stable. And so that means that all these neutrons, decay quickly via beta decay, giving you this huge amount of electron antineutrinos. So here's the broad picture about JUNO. So it's a multi-purpose experiment that's currently under construction still, although construction is nearing the end, as I will tell you a little bit later. It's a big sphere, as you can see here, containing liquid scintillator, surrounded by ultra pure water, shown here in blue. And it's, let me go back to what I said about the liquid scintillator, is 20,000 tons or 20 kilotons. So it's by far the largest liquid scintillator detector ever built in history, by more than a factor of 20 compared to what would be the second place. And one of the important things is, of course, it's underground. I will talk briefly about all of those details later on. But one important thing to remember is that JUNO is at an equidistant from 8 nuclear reactors, because again, remember, JUNO is primarily designed to measure nuclear reactors. And so it's at 52.5 kilometers from 8 nuclear reactors in 2 different power plants. Only in China can you do this, as you can imagine, because there's a lot of nuclear reactors there. And it's, as I mentioned, 700 meters underground. One important feature to remember about JUNO is that it's going to be able to measure the energy resolution of reactor antineutrinos and other low energy particles with really good precision. So with really good resolution. It's going to be 3% at 1 MeV, and I will explain why we need this good energy resolution in a second. Just to motivate the location of JUNO, because you might be wondering why 52.5 kilometers, right? This is not an accident. It's because we need to be here, basically. Again, I hope you can see my mouse. This is the oscillation probability for the disappearance of electron antineutrinos. And as you can see here, it contains a lot of oscillation parameters. That means that with this channel, the electron antineutrino disappearance channel, we have access to all of these oscillation parameters, so that's great. And depending on which parameter you're zeroing in, that drives your choice of baseline. So there's been other reactor experiments, most of them much closer to the reactors, with the exception of Camland. For example, Diabay, those detectors were much, much closer to the reactors because I say we because I am still also a Diabay collaborator. We were trying to measure theta 1,3 very precisely. So we're trying to be at the location of this dip that you can see here. And so it's the best thing to do is be very close to the reactor. That way you have very, very high statistics. You don't need huge detectors in that case. And you can measure this disappearance here very precisely. You can make a very precise measurement of theta 1,3. However, JUNO wants to observe everything at the same time, because not only do we want to measure these parameters, we also want to determine the mass ordering, as I will show you in a little bit later on. And so for that measurement, we absolutely have to be here. And so that's what drives the choice of baseline. And having established the baseline, since it's pretty large, that means we need a huge detector. That's why the 20,000 ton detector. Now, one more quick thing to emphasize here. So we're going to see the effects of all of these oscillation parameters simultaneously. JUNO is going to be the first experiment to actually do so. And as you can see here, there's no dependence on theta 23 or delta CP. And so that's, again, pro or a con. Let me frame it as a pro. It means we can make these measurements without having to worry about these other parameters, whereas other experiments do have to disentangle the effects from all of these other parameters when they do those measurements. Okay, how do we detect neutrinos in JUNO? We use the inverse beta decay reaction, where you have the electron antineutrino interact with a proton, give you a positron and a neutron. This reaction has many advantages. Relatively high cross-section is one of them. The other advantage is that you get two products that you can detect. So the positron, if you have it in liquid scintillator, is just going to lose its kinetic energy, is going to make the liquid scintillator shine, emit light. Then it gets annihilated with an electron, producing two gamma rays that you can also see very clearly in your scintillator. The neutron just wanders around, it thermalizes, and then it gets captured if you have an element in your scintillator that likes to eat up neutrons. In the case of JUNO, we have hydrogen. And so hydrogen gets excited, you emit. So when the capture happens, you have an excited state of hydrogen, you emit a gamma ray to de-excite. And so that's a characteristic signal that we can also detect. And so the principle of detection for these antineutrinos is the coincidence. We are looking for two flashes of light occurring with a short separation in time and in space. And this greatly allows us to reduce or mitigate the backgrounds in a detector like this. The spectrum, I'm going to be showing you several spectra as we go through the talk. The spectrum looks something like this, curve in blue. It's the convolution of the emitted spectrum from the reactor and the IBD cross-section. So that's why you get something that peaks around 3.5 or 4 MeVs, as you can see here. And I think that's everything I had to say here. So that just gives you the broad perspective about JUNO. Now let me tell you a little bit about what kind of physics we can do with a detector like this, a big liquid scintillator detector underground. So first, let me emphasize something I had already said. JUNO is really multi-purpose. So yes, it's built primarily to measure reactor antineutrinos. We will do so at a rate of about 50 per day. But this is, after all, a neutrino detector that is very good at measuring low energy neutrinos, low energy being MeV or so. And so it's also going to be really good at detecting solar neutrinos. It's going to be really good at detecting geoneutrinos. It's also going to be good, not as good as other detectors that are optimized for atmospheric neutrinos, but we will see definitely atmospheric neutrinos, and we can do some physics with them. And JUNO is also going to be really good at measuring supernova neutrinos, both from a core collapse, where if it were to happen in the next decade or so, which we hope it will, in our vicinity of our galaxy, but also the diffuse supernova neutrino background. I will talk about both of these in a little bit. Also, the big amount of liquid scintillator, the shielding, the overburden, all of those things make JUNO an excellent detector to search for new physics, for example, to search for proton decay, as well as other beyond the standard model phenomena. So let me just briefly go through all of those interesting physics topics that JUNO can do. And let me begin with oscillations, because that's also how I began this presentation. So specifically oscillation with reactor antineutrinos. If there were no oscillations, the spectrum that we would observe in JUNO would look something like this, the curve in black that you can see here. This, again, is the spectrum that I mentioned before that peaks around 3.5 or 4 MeVs. Because we expect to see oscillations, of course, a lot of these electron antineutrinos will disappear, will transform to other flavors. And so we will only detect a smaller fraction of this spectrum shown in black. And so we expect to detect basically the curve, either the blue or the red curve that you see here, depending on what is the ordering that nature has chosen. There's a wealth of information in this oscillated spectrum. And that's what I try to explain here with this, or we try to explain here with this cartoon. The frequency, you see there's two frequencies. There's a wave going on here. It's a slow wave. And then there's a faster wave riding on top of that slower wave. And so those two frequencies correspond or give us information about the two delta m squares. There's two different amplitudes also of the disappearance of these electrons and neutrinos, and those amplitudes give us information about these mixing angles. And then finally, as I already highlighted, the wiggle structure that you get is a tiny bit different between the inverted and the normal orderings. So if JUNO is indeed capable of resolving these features in the spectrum with enough resolution, in other words, if we can measure the energy of reactor antineutrinos with the 3% of 1 MeV energy resolution that I mentioned before, then we will be able to see this little structure and we'll be able to disentangle or to distinguish the two scenarios. Are we in the red? Are we observing the red wiggles, or are we observing the blue little wiggles? And so that means we can determine the mass ordering. And of course, in order to be able to do this, we need a lot of statistics. And so it's going to take time to be able to do this. How much time? It's going to take on the order of 6 years for us to be able to make a measurement to about 3 sigma. Okay. And here I want to emphasize again what I mentioned before. So we're independent of theta 23 and delta CP. We're not relying on matter effects to be able to do this measurement compared to, for example, DUNE. And so that means we're complementary. We're highly complementary to other experiments. If we get the same answer, this gives us increased confidence in our 3 neutrino paradigm. If we don't, then actually that's an interesting question. That means we have more work to do. By the way, since JUNO also is very complementary to other experiments, that means that if we combine with them, we can greatly enhance the sensitivity, because it's not just a statistical addition. We have really different information. And so I'm not going to get into detail, but just know that if you combine JUNO's data with that from other experiments, you can greatly increase the sensitivity, the precision for the mass ordering. Now, as you can imagine, if we can resolve the blue versus the red spectrum here, that means we can also measure these oscillation parameters really well. And that is indeed correct. There's a couple of plots here, but let me just draw your attention to this table here. So this row gives you the current precision for these 4 oscillation parameters. The row below, the one here, gives you the precision that we hope to achieve with JUNO after 6 years. And as you can see, we're below 0.5% for 3 of them. Theta 13, unfortunately, we're not going to be able to do as good as Diabe. This precision right now comes from Diabe. But for these other 3, we'll get this really, really nice precision, which is important for the community because it provides, again, inputs for models. It also provides tests for model-independent tests, or enables model-independent tests of the 3 neutrino oscillation framework.
Problemática.
Sorry, sorry, is there a question? I guess maybe it was just an open mic. I'll continue, but let me know if there's a question.
We don't know if Jose was having a question. Maybe he was going to do a comment. Jose, do you have a question, or do you want to make some comment? No, continue. I think there are no questions for the moment.
Okay, sounds good. So I think I conveyed everything I wanted to convey about this. So I'm looking forward to these precise results on the oscillation parameters. Now, briefly, let me say JUNO is also going to be a really good detector for supernova neutrinos. If we are lucky to have a core collapse supernova in our vicinity anytime soon, within the next 2 decades, then, you know, compared to however many neutrinos we detected in 1987, I think it was on the order of 20, 25. Now with a detector like JUNO, we're going to get thousands, on the order of 10,000. Half of those will be IBDs, the other half will be other channels. And so this is going to give us a lot of information about the energy spectrum, the flavor content, the time evolution of these neutrinos. It's going to contribute. Of course, JUNO would not be the only neutrino detector seeing these neutrinos, but it would provide unique information because we're going to be one of the ones with the best energy resolution and also with the lowest threshold compared to other big neutrino experiments. So it would provide a very complementary data set to that collected by other experiments. JUNO also has some sensitivity to the pre-supernova neutrinos. These are the neutrinos emitted during the collapse. And that would be really interesting because this would allow us, if combining with other experiments, maybe to point in the direction of when the supernova is going to occur. But for us to see these pre-supernova neutrinos, the supernova has to be relatively close. Now, very interestingly, JUNO also will be able to see, we hope, the diffuse supernova neutrino background. So these are all the neutrinos from all the supernovae explosions in the universe. And we expect, of course, here the detection sensitivity depends on the model that you consider. For the nominal model, we expect just after 3 years to get something like 3 sigma. That would be this curve here that I'm highlighting with the mouse. Basically, it's JUNO and Super K with gadolinium. Those are the 2 experiments that will have the best sensitivity to this signal, which has not been observed yet. So this, when observed, I think it's a reasonably big deal, and it provides important inputs to the community. JUNO will also be a good solar neutrino detector. There's unique assets that JUNO has, which is the huge size, the low threshold, and the very high energy resolution that I've already alluded to before. There's some challenges though, and the key challenge is the backgrounds. So I mentioned before how we detect reactor antineutrinos using the IBD reaction, right? And the same is true for supernova neutrinos, or for a big chunk or big fraction of supernova neutrinos. For solar neutrinos, however, the IBD reaction is not possible because the sun emits neutrinos, not antineutrinos. We would need a detector made of antimatter. So we don't have access to that nice coincidence between the positron and the neutron that allows us to separate the signal from the background. Here, we can only use this reaction, elastic scattering on electrons. And so here we're competing with all the backgrounds that are in the detector. And so the way to do this is we call it our singles, all of the signals that basically when we have a flash of light. And so we have not just our solar neutrinos, but we also have a lot of radioactivity, for example, happening in here. And by looking at this aggregated spectrum, we need to disentangle the little contribution from the solar neutrinos, shown, for example, in these multicolored curves here at the bottom. And so still, JUNO is able, or is going to be able to do a nice job with solar neutrinos. We're going to be able to collect a large sample of boron-8 neutrinos. These are the higher energy solar neutrinos. And so no problem here because we compete less with the backgrounds because they're higher energies. And for the low energy solar neutrinos, specifically beryllium-7, PEP, CNO, we hope to be able to do better than Borexino. So Borexino is currently the world-leading solar neutrino experiment. And so the Borexino limits or measurements are shown in this line here, these dashed lines. And so we hope to be able to do better, but it depends on how clean our scintillator will be because of what I said about the backgrounds, right? The more we manage to reduce the backgrounds, the better we can pick up all of these signals that are in there. So we'll see. But again, we're hopeful that we'll get really good scintillator radio purity and be able to make these measurements really well. Finally, JUNO will also be a really nice detector for geoneutrinos. So because of the size, again, it's 20 times bigger than CAMLAND, which would be the second largest liquid scintillator detector. We're going to get more than 400 geoneutrinos just in 1 year. And that is already a bigger sample than what CAMLAND and Borexino have accumulated throughout their entire lifetimes. So just in 1 year, we collect largest available sample of geoneutrinos available. The challenge for JUNO is that we have a lot of reactor antineutrinos. That's, of course, a good thing because we also, as I mentioned before, we are trying to measure reactor antineutrinos. But for the neutrino measurement, that's a background. And so despite the fact that we have a large amount of reactor antineutrino background, we still can pick up this geoneutrino contribution pretty well. And so in just 1 year, we will get a measurement comparable to what Camlin and Borexino can do or have done. And on the scale of 10 years, we'll basically half it. So JUNO will be the world-leading geoneutrino experiment for the long term, unless another experiment comes online that is able to do better. And JUNO will not only be able to measure the total geoneutrino signal, but also separate the components, the thorium and uranium, and also to measure this ratio. Finally, here, I just highlight how JUNO is also good at searching for proton decay, specifically in modes where we have a triple coincidence. Again, because of backgrounds, we want to look for these signals when we have coincidences of events in time and in space. 3 signals happening very succinctly and also very close to each other, basically. And there's 2 specific modes where we can see this happening. So we have the kton decay mode for proton decay, where the kton, we see it. Normally, you would not see this in a Cherenkov detector because of the threshold being different in a water Cherenkov detector, but in liquid scintillator, we will be able to see it. Then it decays to a muon, and then that gives you a Michel electron, and so we see the 3 signals. We get a pretty good sensitivity, comparable to what Super-K has done over now decades. There's another mode that's really interesting, is the invisible decay mode, where you have, for example, nucleon decaying into 3 neutrinos, anything that's invisible. And here, again, you might be wondering, how can you see this? But of course, we don't see the 3 neutrinos. However, we see the excited atom that was left over after this decay. It has a chain of decays that we can detect. Again, gives us a triple coincidence. And JUNO, when it turns on, it'll automatically just give you almost an order of magnitude better result than the existing limits for this specific type of decay, which come from Camlin and from SNO+. Okay, so I already gave you a big picture about JUNO, how it works. I told you about the kind of physics that we're going to do with JUNO. Now let me just talk a little bit more about the implementation. How is the detector designed, and what is the status of it? So here again is another picture just to remind you how JUNO works. Is this big sphere surrounded by a lot of photomultiplier tubes to detect the light of charged particles interacting in the liquid scintillator. We have over 40,000 photomultiplier tubes because we need, again, this very high energy resolution, surrounded by ultra pure water. So in order to fulfill the physics goals that I just went over a few minutes ago, it's clear that we need very high statistics. We need to be at the right baseline. We need to have this really good energy resolution. We need to control our energy response systematics really well, and we need to reduce our backgrounds as much as possible. And so as I describe the design of the experiment in the next few slides, you will see how we tackle, I'm not going to go them one by one because there are different aspects of the design that maybe tackle 2 or 3 of these simultaneously, right? So just keep this in mind as I describe how the detector is constructed and designed, that we're trying to tackle these keys for making successful measurements, successful physics. And let me highlight something I already mentioned before, JUNO. Just how do we get the high statistics? We need to be close to many reactors, and we need a huge size. That's why JUNO is 20 times bigger than all the previous liquid scintillator detectors that have been built. A few words about just the project. The collaboration is big. There's more than 650 of us working on this project from over 70 4 institutions in 17 countries or regions. And here's a photo of the collaboration taken not so long ago. Let me tell you a little bit about the civil construction for the detector. So it started in 2015. It took 6 years, roughly, to be fully completed. It was a challenging operation because, as I already explained, JUNO has to be at exactly 52.5 kilometers from 8 nuclear reactors. And as you can imagine, at exactly 52.5 kilometers, there was nothing. There's just some mountains in the Guangdong province. And so we had to put the detector there and only there, or else we cannot measure the mass ordering. And so we had to create an infrastructure from scratch. We have our own campus. All of this is JUNO, basically, and the detector is underground. You actually go through one of these doors and it takes you on this little train that you can see here, and it takes you underground. We have on the order of 200 technicians, engineers, people working during construction at all times in the detector. Let me show you a video of how the detector was constructed. So we started with the outer shell. It's all stainless steel. And then we have this platform in the center that you can see that is starting to go down, as you can see in the video, as the acrylic sphere inside is built. So the liquid scintillator is going to be inside this acrylic sphere that you can barely see here. I'll show you other pictures in a little bit. We build the acrylic sphere from top to bottom. And as the acrylic sphere is built, then we start surrounding it with photomultiplier tubes. That's what you see here in gray. And those PMTs, you cannot see them very well here because they're facing inwards. But from the back, you can see the back of the tubes a little bit, and you can also see a lot of gray because there's a lot of stainless steel there. I'll show you other pictures as we go along, but that just gives you the big picture of how the detector is being constructed. So let me say a few words, a little bit more detail about the construction. So again, the stainless steel was constructed from the bottom to the top. And then once the stainless steel structure was built, the acrylic was built from the top to the bottom. The acrylic sphere consists of 263 panels. They have to be this thick because it's holding 20,000 tons of liquid scintillator. So as you can imagine, it has to be thick acrylic, right? We use a special production line with low backgrounds. And we have the sphere supported or attached to the surrounding shell using these bars that you can see here, for example, here, here, and here, or here, they're shown better. And there's a lot of those bars connecting the acrylic and the structure. So the central detector is immersed in water, as I already explained. Why is that? There's at least two reasons for that. The first one is that the water is an excellent shield against neutrons from radioactivity, as well as, neutrons from cosmic rays and or radioactivity, especially coming from the rock. But also this water, if you instrument the water pool, which we do, you can use the Cherenkov light produced by cosmic ray muons to detect them. In other words, you can use this as a veto system. And so because of these two reasons, the water pool is essential to helping us keep our backgrounds under control. Now, we instrumented with on the order of 2,400 20-inch PMTs. We have some HDPE lining to protect or to avoid radon leaking or seeping into our water, and we expect to have a very high efficiency just with the water itself. But little cherry on the cake, we also put layers of scintillator on top of the whole structure so as to be able to get some really nice tracking for at least a subset of the cosmic ray muons that are going through JUNO. We're reusing this scintillator, by the way, from another experiment called Opera. And then finally, we surround everything with a magnetic field compensating system. It's one big humongous coil, as you can see here in red, that cancels out the magnetic field from the Earth because we want to remove any effects that the magnetic field from the Earth causes on the PMT detection efficiency. JUNO, as I already explained, aims to have a really good energy resolution, never done before, 3% 1 MeV. How can you do that? The first, not sufficient, but definitely necessary requirement to be able to measure the energy of neutrinos very precisely is that we need to see a lot of light. And so here, this table just helps put into perspective how much more light we need and where that extra light is coming from. So I use Jiangmen here as a comparison. Jiangmen used to detect on the order of 250 photoelectrons per 1 MeV energy deposition. In JUNO, if we're going to achieve this 3% in 1 MeV, we need at least 1,200 photoelectrons per MeV. So we need a factor of 5 times more light than what Jiangmen saw. So how can we achieve this? Well, the first thing that comes to mind is let's put more photomultiplier tubes in there. And sure, you can do that, but photomultiplier tubes are circular, and so you're going to have some dead space in between. So you can only kind of double the amount of photo coverage, and so that buys you about a factor of 2 times more light. Is not enough to get to 5. We need a more shiny liquid scintillator. We can get on the order of 50% times more light by making our optimizing our scintillator to be more shiny. We can have a more transparent scintillator. Great. We will have a scintillator that has a greater attenuation length. But even though it's more transparent, since the detector is bigger than other detectors, such as Jiangmen, we still lose light. So we still need another factor of 2. And that comes just from having better PMTs. We need PMTs that have roughly 2 times better detection efficiency than what was achieved with the types of PMTs that were used, for example, in Jiangmen. So I'm not going to go into details unless anybody here is really interested, but we have 2 types of photomultiplier tubes in JUNO, that both of which give us this 2 times better detection efficiency. We have tubes from Hamamatsu, and we also have tubes made by NNVT, which follow a design developed by JUNO. It's just, it was mass produced in a factory, but this was actually developed by us, for us. And we pack them tightly as possible with a very, very small clearance of 3 millimeters, because again, we want to put as many photomultiplier tubes as we possibly can. We have about 18,000 of these large 20-inch PMTs. In addition to the large PMTs, we also have small PMTs, 3-inch PMTs in this space between the large PMTs. And I want to emphasize that Saphir actually played a very important role in building and commissioning this system of small PMTs. And the system, of course, it gives you, these small PMTs give you additional light. That's always welcome. But the main advantage from these small PMTs is that they have different systematics, basically. In particular, they have no charge nonlinearity because they operate in photon counting mode, and so they serve as a reference with which to calibrate the large PMTs. And again, a big thanks to Saphir for all its contributions to building and installing this system of small PMTs in JUNO. JUNO is so big that the electronics have to be underwater, because otherwise we would have 44,000 cables coming up all the way to the surface. The signal would get degraded, and also we put a ton of cables in the detector. There's issues of radio purity and other concerns that we want to avoid. So we instead put the electronics underwater close to the PMTs. For the large PMTs, we have one electronics box that services 3 PMTs. For the small PMT system, we have one underwater box that services 128 simultaneously. And so we do the powering, the decoupling of the signal from the high voltage, and the first readout, the front end readout, here underwater in these underwater boxes. And then we send the digital signals via network cables, Cat5 cables, to the surface. And during the last year and a half, as we've been installing our PMTs, we've been having these light off tests where we just turn off the lights in the entire hall and we turn on the high voltage of our PMTs to make sure everything is working correctly. And this is a photo that we took about a year and a half when we were starting this process. We also have a comprehensive calibration program. I won't get into details again, but basically we have 4 systems. One just deploys calibration source along the central axis, as you can see here. We have another system that takes this calibration source and can put it anywhere in a plane. We have a guide tube that goes around the detector, as you can see here, to reach those areas that we cannot reach with the source. And then we have a remotely operated vehicle that allows us to reach any area we want inside the volume. Let me show you some pictures so you see what JUNO looks like in real life. So just for scale, here are some people and here are some technicians. You can see the yellow helmets installing some PMTs. They're actually installing some small PMTs. I can see the box of small PMTs next to this one right here. So just for scale, this is when the detector was about 60% built or so. And if you zoom in on some of these regions, you can see this box here is one of the underwater boxes with the electronics for the small PMT system, where again, Saphir played a very important role. And you can see these rectangles, these are the large PMT underwater electronic boxes that you can see. And these little discs here are the backs of the PMTs, because of course they're facing inwards. This is a photo taken when the acrylic was under construction. Again, it's a pretty thick acrylic, as I mentioned, 12 centimeters, roughly. And this is another photo when the acrylic sphere was almost fully completed. As I mentioned, we started at the top and finished at the bottom for the acrylic. And so, yeah, you can see exciting time right before the acrylic was completely constructed. I really like this picture. It shows you how many PMTs we packed in this detector. This is the region between the PMTs and the acrylic sphere. Here you see the reflection on the acrylic of these photomultiplier tubes. That's why it looks as if there's tubes here, but of course there's no tubes here. This is just the acrylic. This is where the liquid scintillator is going to go. And finally, this is what's happening now as we speak. We have this layer of scintillator covering the entire detector that is being installed. And again, for scale, notice how there's one person walking in here. This is a big, even though this doesn't cover the full detector, it's still pretty big. It covers about 60% of the detector. So I'm almost done. Let me just tell you where we are in terms of timeline. And let me start with the big perspective again. The whole project started in 2013. The collaboration was established in 2014 or so. The construction, the civil construction started in 2015. And we begun installing the detector in 2022. So it took a couple of years to install the whole detector. Recently, we completed the assembly of the acrylic sphere. And this is a video taken of the cleaning. So in the previous photos that I showed you, you probably noticed that we had this paper covering the acrylic. As you can imagine, of course, it had to be removed, had to be, in some cases, scraped a little bit. And then some very careful cleaning with ultra pure water, high pressure, had to be done to make sure the inner surface of the acrylic was cleaned. And this video is showing you that process. Let me pause here. Now let me zoom in a little bit more to the what's been happening the last few months, basically since December. So December 18 was a very important day for us because that's when the detector was fully constructed, and then the last step was just filling it. Now, you have a few options for the filling of a detector like this. You can try to fill, obviously filling just water on the surrounding and completely empty inside is a no-no because there's a huge pressure differential and it would be a huge risk to the structure, right? So you have to fill inside and outside at the same time. One option is to fill water outside and liquid scintillator inside at more or less the same rate. But after a lot of discussion, we opted for what we think is the safer approach, which is to fill everything with water. So both inside and outside gets filled with water. And then we gradually replace the water inside with liquid scintillator. There's a big challenge here, which is everybody here knows that liquid scintillator is like oil and water is water. So those two have different densities. You know what happens if you put oil in water. It just goes up, right? And so what this means is that in the beginning, when we fill everything with water, the sphere is weighing down. But as we start replacing the water gradually with liquid scintillator, it becomes buoyant. And so it wants to go up. And so the design of the experiment, of course, takes that into account. It is meant to be able to take the difference from weighing to going up. And we're in the middle of that process right now. So we completed the water filling in February 1st of this year. And now we're gradually replacing the water with liquid scintillator. And so here's just a little bit more detail on that. This snapshot, I took it today, as you can see. This is actually China time, so that's why it's already April 10, whereas for us, it's still April 9th. So I took this snapshot, again, just a few hours before giving the talk, and you can see that we are, I don't know, maybe a third of the way along the process of replacing the water with liquid scintillator. Okay. We hope to finish by July of this year, roughly July, August. And at that moment, we'll have our full detector ready to do physics. And so it's a very exciting time for us. So I'm almost done. I know it's already been 1 hour. We started a little bit late, but still I wanted to finish on time. So let me just mention very quickly, we have a mini JUNO next to one of the 8 nuclear reactors. It's called Tau. And it's going to allow us to make some measurements of the spectrum of reactor antineutrinos, as well as to do other physics. And I'll just leave it at that. And so, yeah, let me just summarize and conclude. So we have this multi-purpose neutrino observatory, has a rich program in many areas of neutrino physics and astrophysics, can do all sorts of things. JUNO is really pushing the limits in terms of liquid scintillator detection technology. It takes the technology that has been used in previous experiments like Diabay, like Hamland, but then it really pushes it to the limit in terms of better PMTs, more optimized liquid scintillator, how to construct such a big detector. Nobody has ever built an acrylic sphere that is this large, for example, etc. And as I just mentioned, we're expecting to begin physics data taking very soon. The construction of the detector is now done. We're in the filling process. We're expecting to finish filling around this summer. So we anticipate some results, hopefully some surprises, as is always the case. And so, yeah, thank you for your attention. Stay tuned. I hope maybe in another occasion I can present to you, or somebody else can present to you, the first results from JUNO. Thank you for your attention.
Thank you very much, Pedro, for the very nice and very complete talk. Question from the audience? Yes, Diego, please.
Yeah, so thank you very much for the nice talk. I have a few questions related mainly with the JUNO Tau detector.
Okay.
So does that detector relies on the same photomultiplier technology that JUNO is relying upon?
Good question. No, not exactly. So in JUNO, we use these large photomultiplier tubes with the little ones on the surrounding. Here we use silicon photomultipliers because it's a small enough detector that we can do so without completely blowing up the price. And so that way we can cover the entire region and we can get a really good energy resolution, even better than the resolution that the big JUNO detector will get. So we expect to get better than 2% at 1 MeV. And so you can see a little bit the silicon photomultipliers here in this photo. Now, let me add, there's a challenge here with using PSIs, which is the noise. So this is why this detector is going to have to be operated at -50 Celsius in order to reduce the dark noise, whereas the big JUNO detector is going to operate at room temperature, 21 Celsius or so.
Okay, can I ask another question? So I understand that the Tau JUNO detector also uses a cocktail, which involves a gadolinium doping plus a wavelength shifter plus a fluor. So
PPO.
when you, yeah, PPO, exactly. So when you produce light within the detector fiducial volume, some of that light, I understand, is reprocessed by the wavelength shifter towards regions of the spectrum that correspond basically to visible light. Is that correct?
There's a little bit of component into visible light. You can actually see a little bit, but it's optimized to be the type of light that is best detected by photomultiplier tubes, or in this case, SciPMs. So you're absolutely right. That wavelength shifter does that shifting, and precisely we try to match it to our photo sensors as best as possible.
Okay, so if I have a signal of, say, two back-to-back photons producing, say, a decay, and those two back-to-back photons are in the order of a few MeV, will I be able to observe the flash produced by those photons when they reach the photomultipliers? So I'm speaking about order 3-4 MeV photons.
Yes, absolutely. I mean, that's exactly the type of signal that we definitely want to make sure we catch in both JUNO tau and the big JUNO detector, because every time we get a positron, we will have an annihilation into 2.5 MeV gammas. And we definitely want to see that signal. So the answer is yes.
But so it's just the point is that I'm currently working in a project in which I have been trying to determine the capabilities of the JUNO tau detector for detection of action-like particles produced in nuclear reactors. Okay, so that's why I'm asking this question, because for quite a while I have been wondering to whom I can ask this question, and it happened that you were giving this talk, so I thought it was a great chance for me to ask. My question is, if you produce these photons, do these photons reach, because I understand that the cocktail involves linear alkylyl benzene.
Yes, that's the solvent.
So, yeah. If I produce this light in a certain point within the fiducial volume, does that light reaches the photomultipliers without being reprocessed whatsoever, or it goes through a kind of reprocessing by the liquid alkylyl benzene, or the cocktail in general?
Okay, I think I understand your question. Let me know if I misunderstood. But so the original gamma, what it's going to do is it's going to bounce around, and it's going to Compton scatter. And when it Compton scatter, it's going to pass some of its energy to electrons. And that's actually what you're seeing. You're seeing those recoiled electrons as it goes. So there's a probability, there's a non-zero probability your gamma will escape or partially escape before it has deposited all of its energy in the volume. So we call this energy leakage, and it's a real effect in JUNO tau. It's a much smaller effect in JUNO, because in JUNO is so much bigger that the probability of it escaping is much smaller.
I see.
So I don't know if that answers your question. This can happen, and there's a probability for it to happen, and it depends on what direction the gamma, the initial gamma, is going in, and how close to the edge you are.
Okay. Is there documentation on that you can probably later on email me or point me to, please?
There must be, at the top of my head, I don't know exactly where, but for example, the JUNO tau CDR, the conceptual design report, must cover energy leakage in some detail.
Okay,
we can talk offline. Maybe I can help you.
That will be great. That will be great.
Yeah.
If I don't know whether I'm allowed to ask a last question, Antonio.
No problem with me. That's up to Antonio.
Okay.
Yes, sure. Please, if you want to ask more questions, feel free to.
Okay, thank you. So, what is the capability of the tau JUNO detector for detecting scintillating light produced by nuclear recoils?
Very little. Nuclear recoils like the type you would have in, for example, a dark matter interaction or something like that, right?
Yeah.
Very, very little, because those are very, very low energy signals. And yeah, we're almost blind to that kind of signal. Again, I'm thinking low energy nuclear recoils like the type you are searching in a direct dark matter detection experiment. Very little.
Yeah. I had a kind of naive idea. I don't know whether this is feasible. So I'm thinking about order 5 keV nuclear recoil energies, so very low energy. So I calculated the light yield for that, and the light yield for a single event is very small.
Yes.
But then I thought that if I have a collection of events happening in a time window, say 1 minute, I might be able to collect enough light from all the single events which produce little light, so the integrated light is enhanced and then produces a sizable signal. Do you think that is feasible? I don't know whether I'm explaining myself properly.
You said 1 minute, and to me that sounds like an eternity.
Yeah, I know, because I know that they are speaking about nanoseconds. Yeah, of course. Yeah.
So I'm skeptical.
Yeah. So the photomultipliers cannot be tuned to make measurements, at least for a while, or a 1 minute time window, so they can collect all this light which is produced by the single events with very light yield, each one, but such that the sum of all the light yield becomes sizable.
The photomultipliers can see this. The problem is it requires lowering the threshold very much. And as you lower the threshold, you also absorb all these kinds of backgrounds. So that's why you cannot go arbitrarily low in threshold. That's the problem that I'm thinking of. Maybe I'm missing something in how you're framing the problem, but that's the problem. You can see the light. It's just you have to go really low, and you take also all kinds of junk, all kinds of radioactivity, and all other things, many other things that happen at low energies. I
see. Because what I found was that at least when you have these nuclear recoils and this kind of events that I'm looking at, so you have the scintillation light produced by the nuclear recoil, but then you have a final state photon. The final state photon produces a prompt signal, and the scintillation light produces a delay signal. Okay. So I thought that it could be done, the detection of this kind of interactions in the same way is done with neutrinos, inverse beta decay detection.
If you have a coincidence, that greatly helps. But if one of those two signals is very low energy, then we have this problem about the threshold.
Okay.
But of course, the coincidence would help greatly.
Yeah. Okay, so I'm asking this because I'm finishing a project in about the capabilities of this detector, the tau JUNO detector for this kind of searches, actual like particle searches, and yeah. So I don't know whether actually we are gonna submit before asking a JUNO expert to tell us whether what we are saying is feasible from the experimental point of view.
Might be a good idea to do that if it's okay with you. Yeah, I can help you either myself take a quick look or put you in contact with somebody who can help take a look. If you're willing to do that,
we will very much appreciate that. Thank you very much. Thank you.
Pleasure.
Any more questions from the audience? Pedro, Juan, I had a question. You mentioned around the middle of the talk that for the reactor missing angle, the precision cannot be improved with respect to diabase, whereas the other neutrino missing parameter and CP phase, the precision gets significantly improved. What is the reason why the reactor missing angle, the precision for the reactor missing angle cannot be improved with the other neutrino missing parameters?
Yeah, good question. So it's still a pretty good measurement. What JUNO can do is just diabase can do much better. And it has to do with statistics ultimately. So in diabase, we are very close to the reactor. And so we can map out this drop to exquisite statistical and systematic precision. Also, we do a cancellation of near and far systematics. We have 8 detectors in total, and so we do a cancellation of systematic uncertainties this way. In JUNO, we need to map out, so the size of these wiggles is what gives us theta 1,3. And as you can imagine, since we need a lot of statistics to be able to see the troughs and the peaks enough to be able to make this measurement. And so we're just not going to collect enough statistical precision to be able to see this amplitude with as good of a precision as diabase.
So maybe in some year, I don't know, maybe 10 years or a bit more, this precision could be improved in principle after taking some of the statistics.
So definitely more time helps. Here you can see how the precision improves with time. Theta 1,3 is the one in black here. But of course, at some point, systematics start catching in. And so that's why the dash curve here is just statistics. In principle, you always get better and better and better, but it takes a lot of time, as you can see here.
Oh, it's
And
too
then
much.
at some point, yeah, so this is 10 to the 5 days. I mean, we're never going to run for that long, I don't think. And before we get there, the systematics start catching up. Yeah.
Thank you. Thanks a lot, Juan. Any more questions? More questions from the audience? If there are no more questions, we thank Pedro for the excellent talk, very complete and very excellent talk. Thank you so much, Pedro.
Thank you, everybody.
Thank you very much. Thank you.
Thanks a lot, and see you at the next seminar. See you.
Bye-bye.
Bye.